What's up, people? This is your man's Technology G, or you can just call me Tech G. So in this video, you're going to learn about various notational systems such as binary, hexadecimal. You're going to learn about decimal, in addition to learning about how data is represented in forms called ASCII and that of Unicode. All right, so let's get to it. So first things first, binary. So in mathematics and digital electronics, a binary number is a number expressed in the base 2 numeral system, or simply referred to as the binary numeral system. This system uses only two symbols, typically the number 0 and the number 1, to represent for off and on, respectively. This number system is the basis for all binary code, which is used to write data such as computer processor instructions for every piece of data that is essentially processed. So if we look at this chart over here, you'll see on the left-hand side, you have numbers that represent decimal numbers going from 0 to 15. And on the right-hand side, you have a representation of binary. Binary basically is how a computer reads information. It takes a bunch of information and converts it into a bunch of zeros and ones, like I said, that represents on and off. And what you're looking at on this chart here is basically binary for one quote unquote octet, I guess you could say. And each octet consists of 8 individual bits. Now, depending upon which bit is turned on is going to represent its decimal equivalent. So if you look at the decimal number 0, that means all of the 8 bits are turned off. If you look at decimal number 1, that means the first 7 bits are turned off and the last bit is turned on. And the last bit represents the number 1. Now, when you get to these 8 bits, basically what this is trying to say is the very first bit at the very end of the chart represents the numerical value of 1. The second bit will represent 2. The third will represent 4. Then you will go to 8, 16, 32, 64, 128, so on and so forth, right? So depending upon what bit you turn on is going to represent its decimal value. So if we look at the decimal value of number 2 here, you'll see we have 6 bits turned off, which represent 0. Then when we get to the 7th bit, it is turned on, showing you signified by the number 1. And then we have the 8th bit turned off. So being that we have that second bit turned on to number 1, remember that second place value represents the number 2. If you go all the way down to, let's see, is it on this chart? I don't think I have it on this chart. I'll show it on a few. Okay, matter of fact, if you go all the way down to the decimal equivalent of the number 15 at the very bottom, you'll see that the first 4 bits are turned off and the last 4 bits are turned on. Now, if you take the last 4 bits, 1111, and you put them into their decimal equivalent, that'll be the number 1, 2, 4, and 8. If you add 8 plus 4 plus 2 plus 1, that'll give you the decimal value of 15. I know it sounds confusing, but remember, you don't have to get into grave detail when it comes to this particular IT certification. You just have to have a familiarization with these concepts, ladies and gentlemen. So, how does binary work? Glad you asked, ladies and gentlemen. So the zeros and the ones in binary represent off and on respectively, like I said earlier, meaning there is no flow of electricity moving, which is the number 0, or there is a flow of electricity moving, which represents the number 1, or the binary digit number 1. The flow or restriction of the flow of this electricity moves through a component which is known as a transistor, which is the primary building block of all microchips. Now, depending upon the arrangement of the transistors, these things called logic gates are created, which essentially tell a computer to either pass a current of electricity, which would mean that it is turned on to the value of 1, or to restrict a current of electricity, which means that the value number of 0 will be turned on to prevent this information from flowing. What is base 10? So we're still talking about notational systems here. So to truly understand how binary works, we must first discuss a numbering system known as base 10. Now, if you ever used your fingers to add numbers up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, things you should have learned in kindergarten, then you were already using the concept of base 10. You're using stuff to count with your fingers, or you're just counting random objects. That's base 10. Basically, numbers 0 through 9 is the base 10 numbering system. And this also includes decimal numbers as well. All right, so now we're going to talk about the next notational system, and that is called powers of 2. So by definition, in mathematics, a power of 2 is a number of the form 2 times the letter n, where the letter n is an integer, which is the result of an exponentation of the number. I know it sounds a little bit confusing, but it's really not that confusing. So in layman terms, basically what I'm saying is this. Powers of 2 is simply the mathematical doubling of numbers, starting with the base number of 2. So if we look at the chart here, we got the decimal number 2. And I've already explained to you its binary equivalent, which is 10 or 1, 0. Now, if we want to write 2 out in exponential form, that'll be 2 to the first power, and then that'll result in the number 2. If we go to 4 written out in binary is the number 100 or 100. If you want to figure out the exponential form of the number 4 based off of the number 2, that'll be 2 squared, or 2 to the second power, which is 2 times 2. And we can just keep going on and on down the list. If we look at the number 8, that 8 written in binary is the number 1000 or 1000. Also, 8 written in exponential form when using base 2 or powers of 2 is 2 cubed or 2 to the third. And you see it written out in its multiplication form, 2 times 2 times 2 equals the number 8. And you could just go on and on down the list. That is how powers of 2 work, ladies and gentlemen. Next, we have hexadecimal, also known as base 16 or simply hex. And basically, this is a positional system that represents numbers using a base of 16. So base 16 notation uses the following digits: 0 through 9, which are equivalent to values 0 through 9 in decimal notation. So the numbers 0 through 9 is the same in hexadecimal notation. Now, when you get to the symbols, letters A through F, they are going to be equivalent to the values 10 through 15 in decimal notation. And so in hexadecimal, you will have a grand total of 16 digits, starting with the number 0, going all the way to the symbol F. Every hexadecimal digit is the equivalent of 4 bits in binary notation. And a bit is also known as a nibble. But hexadecimal is used quite commonly in the computing world, such as expressing color values when it comes to something called hypertext markup language, or most of you are familiar with this simply as HTML. And basically this type of stuff is used across various mediums, all the way, like I said, from the internet all the way to IP addressing schemes, particularly those dealing with IP version 6, which I'll discuss in a few minutes, and all the way down to this thing called a MAC address, or a media access control address. Basically, this is like an identification put onto every device in the world that has connectivity to the internet somehow, some way. All right. So let's see. So let's get back to this chart over here. So we got decimal, binary, and hexadecimal, right, on this left-hand chart. So if we go down and we look at the number 15, decimal number 15, you'll see that it is written in binary as 4 ones, 1111. Like I said, if we go back to that other chart, I don't think I have it up. But anyways, if we go back to that other chart, if you guys recall what I said those basically represent the first 4 bits in an octet that are turned on. So the first bit of 1 is turned on, the second bit of the number 2 is turned on, the third bit of number 4 is turned on, and the fourth bit of number 8 is turned on. If you take the numbers 8 plus 4 plus 2 plus 1, that's going to equal the number 15. When you convert that over into hexadecimal, if you look at the chart on your right-hand side, you will see that the value F, or the number 15, represents the value F in hexadecimal form. Like I said, you don't have to be subject matter experts with this. You just have to be familiar with the concepts, at least as far as this exam is concerned. All right. Other places we see hexadecimal values is when it comes to color values, ladies and gentlemen. So when you're looking at your computer screen or your television screen or your smart screen, you are basically looking at a spectrum of colors being represented by a mix of what is called RGB, or red, green, and blue. You're just looking at a mix of primary colors. So, for example, the hexadecimal color code for red would be FF with 4 zeros. That, if you type that actually into Google, it'll pull up a picture saying that this is what the color red looks like when you convert it into its hexadecimal equivalent. Blue would be 4 zeros and 2 Fs. White would be 6 Fs. And then black would be 6 zeros, right? Which means that there is basically none of these colors are showing up. Essentially is what black means. You're just going to be looking at black. Now, when it comes to white, where you have 6 Fs, basically that means all the colors of light have been mixed together to produce the color white, which comes out to be FFFF. Now, if you want to start dibbling and dabbling in secondary colors like the color orange, then, you know, basically that's when you mix whatever 2 colors it takes to make orange. I can't think off the top of my head, but at least when you type it into Google, this is what the hexadecimal value for orange is going to be. It's going to be FFA500. All right, we're going to talk about IP version 4 and IP version 6 addresses, ladies and gentlemen. So basically, if you are trying to get access to a certain website, most of you are familiar with just typing in the name of a website like Amazon.com or YouTube or Facebook or whatever it is that you look at, right? You know, what most of you are probably unfamiliar with is that the name Amazon.com is directly tied to a number system used to help locate that website. That numbering system is called an IP address, which stands for Internet Protocol Address. And IP addresses come in 2 different protocols. The first protocol is called IP version 4, which looks like this IP address I have here on my screen of 172.16.254.1. Each of those dots represents an individual octet, in case you guys were wondering what an octet was when I mentioned it earlier in the slideshow. All right. So anyways, the IP address, what happens next is this IP address is then compared up against, compared with the name that is stored in what is called a DNS, a domain name server or a domain name system, depending upon what you want to call it. The easiest way to think of a domain name system is every last one of us has an iPhone, right? Now, how many of you out there have actually memorized people's phone numbers? Like back in the day, we used to have to memorize phone numbers. Now, what do most of you guys do? When you get a phone number, you'll type in that person's phone number, and then you'll assign that person a name. Mom, dad, food, gym, work, boss, whatever the case may be. So next time you want to call up your mother or your father, most of you guys are not reaching into your phone and dialing up their number by punching the number in. You're just going to scroll through, look for mom, hit mom, boom. It's going to automatically route you to that phone number and start ringing your mother or your father's cell phone number. That is essentially how IP addresses work, because essentially none of us have the patience to sit around here and memorize IP addresses like 172.16.254.1. But we can remember yahoo.com, Google, Facebook, Amazon, such and such. So basically when we type those names into what is called a URL, a universal uniform resource locator, it takes Amazon.com, goes to this quote unquote phone book, matches that name up against the IP address, and then routes you all the way to that website server so that you can go out there and do whatever it is that you were intending to do with that website. That is essentially in a nutshell how a domain name server works, right? Now, when it comes to IP4 addresses, there are 4.3 billion IP addresses in the world. Now, I know that seems like a lot, and at once upon a time, we all thought that that was enough IP addresses to cover every device in the world. That is not the case, ladies and gentlemen. Why? Because every day there is some new piece of technology coming out that can connect to the internet through some manner, whether it's your phone, whether it's a component of your car. You got refrigerators and washing machines that can connect to the internet using this concept called IoT, the Internet of Things. The webcam you're looking at me on, all this stuff. All of this stuff that needs to connect to the internet, they all have to get assigned an IP address of sorts in order to allow for it to go out there and do what it's supposed to do when it's time to get you out there surfing the World Wide Web. So, being that that is the case, we simply ran out of IP addresses because we have too many devices that are trying to connect to the internet. So, how did we solve that problem? Well, we came out with a concept called IP version 6. And IP version 6, what you're looking at on your screen is this is an example of an IP version 6 IP address. Now, can you imagine sitting around here every time you wanted to visit a website, you'd have to type this long character string into your URL to visit Facebook, Amazon, or whatever site that you're going to. Who in the world are going to sit here and try to memorize all these numbers? Not me, and definitely not you. But we can memorize Amazon.com, Google, Yahoo, YouTube, et cetera, et cetera. And then, like I said earlier, the DNS will take that name, match it up against this IP address that's stored into a machine somewhere on the internet called the DNS, and then it'll help forward you to that website so that you can go out there and do whatever it is that you're trying to do. Now, when it comes to IP version 6 addresses, there are currently 340 undecillion addresses. That's a number I'm pretty sure none of you ever heard of. So basically, that is 3.4 billion addresses in the world. Theoretically, we should never, ever, ever have to worry about running out of IP addresses again. But there is a possibility that in the future, we might actually run out of IP addresses when it comes to IP version 6. And some of you are like, how? How is that possible? Well, if scientists ever start perfecting this thing called micro machines, not the little racing cars from back in the day, but micro machines in terms of microscopic robots that can go inside of your bloodstream and repair cells and extract cancer cells and all this stuff that scientists are currently working on. If whatever gets to the point where that stuff is a mass production, this rather large number pertaining to IP version 6 IP addresses might disappear to where we have to come up with another system. Because just think about if you got somebody who's fighting some type of ailment right now, and they decide, hey, let's go ahead and inject a bunch of little micro machines into his bloodstream and go out there and start fixing all the bad cells so this person can get healthy. All of those machines are going to need an IP address. And you think they're just going to stick one microscopic machine into a human? No, they might stick about 100 into that person. So that means they're probably going to have tens of thousands, hundreds of thousands to the millions of these microscopic machines laying around ready to go out there and do whatever it is that they were designed to do. And guess what? They're all going to need an IP address. But right now, we're currently not there in society, to my knowledge. So this 3.4 billion IP addresses for the stuff that you and I utilize in our everyday lives is more than enough IP addresses to make us all happy so we can do what we want to do on the internet for the most part. Now, when we get to looking at these IP version 6 addresses, so basically these things come in what is known as, basically an IP version 6 address is 128 bits long, comprised of 8 16-bit sections. So this IP version 6 address right here that you guys are seeing that starts with the number 2001, if I were to convert every single section of this IP address into its binary equivalent, this is what it's going to look like written out in binary. So you go down to block 1, you see the number 1 with 14 zeros followed by the number 1. That is how you would write the number 2001 out in binary. If you get down to the second portion, the second block where it says 0DB8, in block 2, that is how you will write it out in its binary equivalent. So like I said, once again, an IP version 6 address is broken up into, it's 128 bits long of 8 16-bit sections. So basically you multiply the numbers 8 times 16, you get 128 bits. IP version 4 is essentially just 4 octets, 172.16.248.1. Each octet consists of 8 bits. All right, so now we're going to move on to the decimal notation, ladies and gentlemen. So as mentioned earlier, the most common numbering system used in everyday life is that of base 10. We all have 10 fingers. We all have 10 toes, assuming you were born with 10 fingers and 10 toes, and assuming you still have 10 fingers and 10 toes, right? Base 10 also encompasses the decimal system as well. So when we use the decimal system, we use it to count money. So as you can see in the example on the screen, if you were to write $100.05 out, you're going to actually end up with a decimal number. We use it when we're dealing with percentages. So if you look at the screen again, you have 7.4%. When you write it out in this decimal notation, it's actually 0.0074. You know, the stuff you should have learned in 4th or 5th grade. Also, we use decimals when we are looking at the properties associated with hard drives on our computer system here. So if you look at the screen here, and you see where it says capacity, it'll show something like, I think the screen's a little blurry, but 442, what is that, million or billion something, 442 something, but basically it's showing you how many bytes is written on this drive in this decimal form. And then the other one that circle shows you the byte capacity, written in the drive capacity in binary written out in its gigabit form. So basically decimals are everywhere is what I'm trying to say, ladies and gentlemen. Decimals are everywhere. All right, now we're going to get to data representation. So when it comes to data can be stored, it can be transmitted, and it can also be displayed. The text that you're currently looking at on your screen is numeric codes that are mapped to characters to make them understandable. Now, there are 2 broad categories of character sets that have been used in computer storage, and they are called ASCII and Unicode. ASCII stands for American Standard Code for Information Interchange. And ASCII basically is a 7-bit character set that includes 128 characters, of which 97 of those characters are printable. And these characters include upper and lowercase English alphabet, numbers 0 through 9, and it also includes punctuation marks. So basically, this is one of the first systems to allow for us to type letters that are visible on the screen. We also have what is called ANSI, stands for American National Standards Institute, and this is an extension of the ASCII standard. And this extension allows for us to display things like copyright symbols, trademark symbols, currency symbols, mathematical symbols, and language accents. So this is an extension of ASCII. And it also has 255 characters. Next, we have what is called code pages. So here's the thing. An issue that the standard and extended ASCII characters present is that they cannot display characters used by languages that do not use the Latin alphabet, you know, the letters A through Z, the alphabet that we all learned in kindergarten or preschool, right? Now, to solve this problem for operating systems to work with non-Latin alphabets or to work with Latin alphabets that use accents, vendors produce what is called code pages, which are language-specific collections of characters that are mapped to code. So to explain this in another way, When you are loading up an operating system, so you get you a brand new computer and you got to go through the steps of bringing that computer to life by loading up the operating system. There's going to come a point where this operating system is going to ask you to select the region that you live in and the language that you speak. And based on your response that you enter, the operating system will then select the correct code page for your region or language so that you can get out there on these internet streets and start typing away with no problem. So if you live in so let's just say you live in Latin America somewhere, and you know they always use those letters with the accent symbols over them. Instead of you having to type in a special code or some special characters like we have to do here in America, they could just run through and just start typing on their keyboard, and that A with the accent over it would just automatically appear when they're spelling certain words that has that accent. And finally, we get to Unicode. Basically, Unicode Unicode has replaced the ASCII and the ANSI, which is ASCII extended. And it has replaced it with a print and display language known as Unicode. So Unicode, it supports ASCII, and it also supports the extended ASCII, and it supports both Latin and non-Latin alphabets and special characters. And Unicode supports up to 576 printable and displayable font characters, ladies and gentlemen. So Unicode is essentially the replacement for ASCII. Everybody got that? Good? Cool. All right, now it's time for some check on learning, ladies and gentlemen, and make sure you guys are soaking up this information and getting smarter with every slide that I click. All right, so first question. Decimal 15 is equivalent to which of the following in binary? Would it be 01? Would it be 1101? Would it be 15? Or would it be 1111? If you were to take the number 15 and convert it into binary, which one of these would be the correct answer? The correct answer would be 1111. And how this works is 1111, all of those are bits that have been turned on. Each bit represents the number 8, 4, 2, and 1, respectively. When you add all of those bits up, it's going to equal the decimal number 15. The decimal number 15, when written in hexadecimal, is the value, the letter F. See how that works, ladies and gentlemen? Next question. Which of the following statements is true about the relationship between ASCII and Unicode? Is it A, Unicode contains fewer characters than ASCII? Is it B, all fonts contain the same number of Unicode characters? Would it be C, you can only use Unicode if you are not using a Latin alphabet? Or would it be D, Unicode contains all ASCII characters? The correct answer would be Unicode contains all ASCII characters. So if you guys recall, I told you Unicode essentially replaced ASCII and ASCII extended to make life easier out there for people clicking and clacking away trying to type the little love letters to people up in the DMs. And finally, third question. Which of the following statements is correct about IP version 6 addresses? They are 64 bits long with 8 groups of 8 bits each. They are 128 bits long with 16 groups of 8 bits each. They are 128 bits long with 8 groups of 16 bits each. Or D, they are normally expressed in decimal octets. The correct answer would be they are 128 bits long with 8 groups of 16 bits each. So as you can see on the picture here, we take our IP version 6 address and it's going to be broken down into 8 separate blocks. Each block is going to consist of 16 bits. You multiply the number 16 times 8, and that's going to get you 128 bits, ladies and gentlemen. If you were to take an IP version 6 and write it out in its full, beautiful binary form that none of us want to do. All right. So there you have it, ladies and gentlemen. There you have it. We have discussed notational systems, everything from binary to hexadecimal to decimal to talking about data representation such as ASCII and Unicode. Now, if you want to get more information on this, just visit my website below, technologyg.com. And I have all this stuff on the website written out in beautiful English using Unicode so that you guys can go out there and study to your heart's content and pass this certification. All right, so stay tuned for the next video. Peace.